Hi, everyone. Today we have Quang, who is presenting his work, Multiparty Homomorphic Secret Sharing from Sparse Linear Loading Parity with Noise. Sorry. Quang, go ahead.
Okay, and then you're muting. Okay, awesome. Yeah, so today I'll be presenting my recent work at Crypto 2023. This is joint work with my advisor Ayush, Yuval, Ishai at Technion, and Rachel Lin at UW. Okay. So in this work, we built a homomorphic secret sharing scheme based on a coding theoretic assumptions. And I'll explain all the terms here in a minute. Okay, so to motivate our homomorphic secret sharing scheme, let me start with recalling what homomorphic encryption is. What it is that basically you have this very nice encryption scheme where you can not just only encrypt and decrypt, but you can also homomorphically compute an arbitrary function on the ciphertext. So this evaluation process is completely public, anyone can do it, and then the person with the secret key can decrypt and get the result of the computation. This is a very powerful primitive, first achieved by Gentry in 2009, and with a long series of work since then. And it has also starting to be deployed in practice with several startups and open source projects. However, with this over a decade of work, there are still two fundamental limitations of FHE. The first is that we don't have a good way to exploit the simplicity of the function class in several scenarios. If the function that we're computing is very simple, we don't know of a good way to make the scheme, to make FHE more efficient just based on those classes. And secondly, FHE is only known from lattice-based assumptions, except for very contrived and galactic construction based on I/O and re-randomization, re-randomizable encryption. So could we address these key challenges? Well, in our work, we address these not by looking at FHE itself, but by looking at the weakening of this primitive known as homomorphic secret sharing. It's basically a distributed version of homomorphic encryption, wherein you replace encryption and decryption with sharing and reconstruction. So the workflow looks something like this. You have a client who wants to share her secret input X into multiple different shares, sends it to different servers. Each server will receive one share. Now the server, they can do homomorphic computations on their local shares without needing to interact or communicate with each other during this whole process. And the end result is that you will now get shares of the outputs. And so you only need to collect these shares or even collect part of these shares if we have this threshold, this reconstruction threshold, not to be every party, but just like enough parties. Then we can recover Y, which should be equal to f of X with high probability. And since this is secret sharing, we also want a privacy guarantee, which says that for a given threshold T, we can design a scheme such that any T-1 shares or less will computationally hide the input X. To avoid trivial schemes where evaluation just sort of tacks on the description of the function f, and then reconstruction first reconstruct the inputs and then apply function f to that input. So this is like a trivial construction. So we want to avoid that. And so we have these two extra requirements. First is that compactness, meaning the output shares, basically do not depend on the size of functions. And secondly, in many applications, it's also very desirable to have the reconstruction process be a linear functions. And indeed, our scheme later on will achieve this linear reconstruction property. So that is the definition of HSS. But what can it do? Can it do everything that homomorphic encryption does? Well, not quite, but it can still do a lot of things. In particular, it gives us a way to do secure multiparty computations with reduced or even minimal communications and interaction patterns. This has led to some concrete applications in practice. One such application is private inference, wherein you have a client that wants to query a machine learning model without revealing the query. One way to do this is to split the model into to split the client query into two or multiple parts, send it into different servers, and then the server will compute the response based on their local shares and then send back shares of the results. In this sense, the user privacy of the query will be guaranteed if the servers don't all collude. Okay. An analogous application is anonymous messaging, wherein you want to communicate with someone else where your messages are encrypted and you also don't want to reveal who you're communicating with or who you are to the servers. This can also be achieved if you secret share your messaging queries and send it to separate servers who then compute and then sends back parts of the final message. Another type of applications is in generating large amounts of correlated pseudo-randomness. What I mean by this is that in a setup phase, we can have a short seed distributed to all parties. And then in an online phase, these parties can then expand the seed to have a large amount of randomness that are correlated with each other. And these correlations can be the very useful kind of correlations that you typically need for MPC protocols. These are like oblivious transfer, vector oblivious linear evaluations, oblivious triples, and so on. Okay. So we have lots of applications that are derived from HSS.
Yeah, question.
Yeah.
For the private inference, do you know if this is actually used somewhere already, like if companies already use it?
Let me try to go back. I think like the state-of-the-art private inference sort of use a hybrid. So there's something called a distributed point functions, which is a sort of HSS that is very efficient and it can handle nonlinear operations. And so that's used for handling nonlinear operations, and then linear ones, they just do like normal secret shared MPC. Yeah. Okay. So what has been known about HSS so far? Which HSS schemes have existed in the literature? So depending on the strength of the assumptions, we have HSS for different function classes. If we assume just one-way functions, then we can have these distributed point functions, where this is sort of a dual notion of HSS, where you share your functions and you evaluate shares of the functions on the input instead. I won't go too much into this, but it exists, it's very efficient, and has found practical applications. Okay, going one step forward, we have constructions based on learning parity with noise and variance of it. Here we can handle constant degree polynomials or this class of log over log local circuits. Okay. One step further, if we assume decisional Diffie-Hellman or assumptions or based on class groups, then we can handle arbitrary log depth circuits. And finally, if we allow for lattice space assumptions or I/O, then we get HSS for all functions. One particular aspect that is missing from this picture is how many parties does the HSS scheme supports. And it turns out that prior works have left a two-party barrier in the HSS constructions. And what this means is that all the known previous works, except for those using lattice or IO, could only support two parties. You cannot secret share to three parties or more. You can only share it between two parties. This will limit like the expressiveness and the functionality of downstream applications. Okay, there's sort of an exception with small parties, but really it just relies on the two-party schemes as like a black box. Okay. So this was an open question. Can we achieve HSS that can handle an arbitrary number of parties? Another goal, which seems somewhat surprising, is that even from lattice-based assumptions such as LWE, we cannot support arbitrary thresholds access patterns. Like the best we can do is n out of n. And for some reason, lattice-based schemes, it just doesn't quite work with an arbitrary threshold.
This is because like FHE is not enough for this, but IO is, or something like that.
It's something to do with the noise buildup. Like if it's n out of n, then you can just sort of add everything together. If it's not, then you have to like do some thresholds. Like threshold reconstruction requires like these Shamir coefficients, right?
I know. I was just does LWE imply FHE, or is it because there's some other assumption?
Oh yeah. Oh, LWE implies
So
FHE.
FHE is not enough, but I assume IO is enough.
Yes. Yes. Yeah. IO is sort of a cheat in this situation. So yeah. Yeah, so can we get HSS that has an arbitrary threshold access pattern? And in our work, we achieve both of these things. So assuming this coding theoretic assumptions sparse LPN over some arbitrary finite field, we can build an HSS scheme that supports arbitrary number of parties and arbitrary threshold patterns for the following non-trivial function class. So the class is this class of polynomials with log over log degrees and have a polynomial number of terms. Okay. As a special case, and just to be more concrete, we can support roughly log depth arithmetic circuits. Okay. Our HSS have this inverse polynomial correctness error, which can be made as small as we like, but it must be an inverse polynomial, and with linear reconstructions. Or if we are willing to tolerate nonlinear reconstructions, then we can use error corrections to get down to negligible error. Okay. So that is our main results. And from this results, we achieve two downstream applications. The first is that because we can work with basically any secret sharing scheme as the base of our constructions, we can get an HSS with an optimal download rate. What this means is that we have an ability to pack shares in our HSS. If we have a corruption threshold T that is much lesser than the total number of parties, then we can pack roughly n minus T computation results into a single secret share. The second application we achieved is that we built an MPC protocol where the communications per party scales sublinearly with the size of the circuits for a general class of circuits, not all circuits, but for these layered Boolean circuits. Okay. This sort of circuit size barrier was still an open question before us, and we resolved this for arbitrary number of parties. Okay. So let me tell you now about our assumptions. Sparse LPN, or LPN stands for this learning parity with noise assumption. It basically says that if you have a public matrix A, a secret vector S, and a noise vector E, where E is a sparse vector drawn from the Bernoulli distribution, then A and SA plus E will be computationally indistinguishable to A and a random vector. This roughly says that noisy random code words will look pseudo-random. Okay. A typical setting that we usually see in this LPN assumptions is that this M can be an arbitrary polynomial in the number in the dimension n, and this error rate can be an arbitrary inverse polynomial. Okay, so that was LPN. Sparse LPN is a twist on this assumption wherein the public matrix is no longer uniformly random, but chosen from the set of k-sparse matrices. Each column of A will now consist exactly of k non-zero entries, and the rest are going to be zero. And then we still want the indistinguishability to hold. This assumption turns out to have had a long history of studies in this area of average case complexity and with connections to constraint satisfaction problems. And it has also found prior applications in the past, such as for hardness approximations or cryptographic applications, such as schemes with constant overheads, public key encryptions, or these pseudo-random correlation generators. Another note that I want to make right now is that if you look at this assumptions, one question you might ask is, what is this parameter k? How small can it be? And well, if k is a constant, then there's a subtlety that we need to care about. The subtlety here is that A will now have an inverse polynomial chance of getting two identical columns. When that happens, an adversary can trivially win the distinguishing game of these assumptions. So it may seem that an adversary here will, like this assumption will not hold because an adversary can always have an inverse polynomial distinguishing probability. This is why we did not choose to take k equals a constant here. If we did, then we needed to rely on sort of a special distribution of such matrices, wherein this bad probability happens with negligible chance. But anyways, let's take k to be polylog, right? And what this means is that this bad event here, which I say is high dual distance, this bad event happens with inverse quasi-polynomial probability, which is negligible. And conditions on this bad event not happening, then the best attacks are actually sub-exponential time. These are based on sort of information set decodings and variance. Okay. So this is our assumptions. It has had a long history of study, and we have shown that in this parameter regime that we need in our work, it is plausibly secure, okay, and even post-quantum secure. Okay, so and lastly, this parameter regime is somehow, yeah.
I have a question. What is high dual distance?
Yes, I should get to that. So basically, let me, yeah. So when I say dual distance, I mean like you take vectors x such that ax is equal to 0. So vectors in the kernel of A. And the dual distance is the smallest Hamming weight of such a vector x. High dual distance here means that any such vector x will have omega 1 Hamming weight. So like in this identical column case, it means that we have a vector x in the kernel of A such that it is has a Hamming weight of 2. But we also need to rule out Hamming weights of 3, 4, 5, and so on. Yeah. me move on. Yeah. So this will be at the end of the talk where I'll say, well, tell you why this parameter regime doesn't seem to imply PT. Okay. But first, let me get to the HSS construction. Okay. So in our HSS, let me start by recalling this sort of TLFN Shamir secret sharing. And basically what it is that each party will hold, well, this also holds for any linear secret sharing. I'm just saying Shamir as an example. And for any linear secret sharing scheme, we can evaluate linear functions on the secret shares in a local manner, right? The parties basically just need to add, perform the same linear combinations on the secret shares. Okay, so linear operations is not a problem. The real problem is how do we handle nonlinear computations? Concretely, if you were to share, have like secret shares of X and secret shares of Y, how do we get secret shares of X times Y without communicating anything? Okay. So the key idea in this first work that introduced an HSS scheme is that we have a share conversion process that can go from the secret share of some value Y to the secret share of Xi times Y, where Xi is one of the shares that were shared at the beginning. And this requires some helper information, which I'll talk about in the next slide. But assuming this process works, then what we can do is, let's say we want to compute a monomial, that is xi1 times all the way to xid. We can use this share conversion process d minus 1 times to eventually get a secret share of the product yd. Okay, so that gives you a monomial, and then you can just add all of these monomials together to get an evaluation of a polynomial. So we have reduced our task to basically this share conversion process. So what are these helper informations? They will include an encryption of the input values. And here we will instantiate encryptions with this sparse LPM-based encryptions, where you basically have a k-sparse vector AI, and then this inner product AI S plus some noise term EI plus the input XI. This is not quite enough, and this is why we need encryptions of XI times Sj for all I and j. So basically multiply each input with each coordinate of the secret vector. Okay, and then we also have some base secret shares, xi and xi times sj. During this share conversion or homomorphic evaluation process, we will keep an invariant. The invariant is that for every intermediate computation y, we will maintain a secret share of y and a secret share of y times sj for all j. We can see that already at the base level, where with all these inputs xi, this invariant is maintained. So how do we do this share conversion process? Well, given these helper informations and the secret shares of y and y times sj, we can do the following. We can multiply the second part of the ciphertext with the secret share of y. When you expand this out, you get first term that is inner product times y, second term is some noise term, and the third term is what we want. We want xi times y. So now we need to get rid of the inner product term. And we can do this by computing it in another way. We can compute it as the inner product of the first part of the ciphertext, this vector AI, with the vector of the secret share y times sj, when you expand this out, you will get the exact same inner product term. And also, this is not a very dense sum. It is actually a sum of at most k elements, right? Because this vector ai is k-sparse. So that's what we get. And when we subtract, we get some noisy shares of xi times y. Okay, now we do the exact same process to get from shares of y times sj to xi times y times sj. We basically just put y times sj. We basically just replace the ciphertext I with ciphertext ij. There's sort of a typo there with it's supposed to be bij times secret share of y, but it's completely analogous. Okay. So that's roughly how the share conversion process works. But does it really work? Well, what I showed you is that at each level, we have some accumulation of noise terms. We don't get the secret shares of y exactly, but we get y plus some noise term. This noise term is sparse, meaning that with some probability, there will be noise, but with high probability, there won't be any noise. So how much is this noise going to accumulate throughout the process? And well, let's try to analyze this. First, we can see what happens in this share conversion process. This was, I just copy pasted from the previous slide, but this is somewhat inaccurate. It's inaccurate because, well, if y is some intermediate value, then it must have also come with it some associated noise. So we have to take that into account as well. So when we take that into account, we have new noise terms. But luckily, the new noise terms are not too much. And this crucially depends on the fact that we have a k-sparse vectors. And so this is only a sum of k prior error terms. Thus, each conversion only increased noise by a factor of roughly k. And so when we compute a degree d monomial, you have k to the O of d times the initial noise rate, which is n to the minus delta, in some inverse form of it. Okay. So because we could limit the noise growth in this way, we can now calculate how much, what is the maximum degree at which we can evaluate our scheme. So we basically just need to set up this equation. We start out with the initial noise rate, n to the minus delta, times the growth factor, which is k to the OD, and times the number of monomials. And you want all of that to be less than some inverse polynomial in the security parameter. And this leads to the degree being log over log, the number of monomials being an arbitrary polynomial, and the sparsity k itself being polylog n. And this all works out. Okay. And yeah, I just want to say, if we are willing to assume sort of a more wacky assumption with constant k, then we can handle up to log degree.
Wacky assumption being that A is somehow modified so that the
Yeah.
columns aren't independent.
Yes. So like A is sample from a special distribution.
Is the special distribution? Oh, sorry, it's not enough to just say sample each fresh column conditioned on not being any of the other columns, because you need this dual distance thing.
Yeah.
You do something weird.
Yeah. It's not clear how you would do that in polynomial time.
I see.
Like the procedure that you mentioned, it would take super polynomial time because you want to rule out high dual distance for every constant.
Yeah.
Yeah.
No, I guess I was just saying it's not just repeated columns, it's the dual distance that you need to worry about. Like repeated columns is one way for the dual distance to be low.
Yes.
But others,
Yeah. Cool. So that is our HSS. Let me just point out a few, I guess, comparisons with prior schemes. And of course, if you don't know about prior schemes, then yeah, you basically don't need to know. What I do want to say is that here's how we avoided the prior two-party barrier. This barrier was because of this distributed discrete log procedure. And yeah, there's just no way that procedure could work for more than two parties. And we completely avoid that, and which means our scheme can handle arbitrary number of parties. It can also work with an arbitrary linear secret sharing scheme. We basically take any such scheme, and using our HSS sort of compiler, we can make it to have some homomorphic capabilities. So yeah, it gives us arbitrary number of parties, arbitrary thresholds, and it also leads to this optimal download rate using a packed version of secret sharing. A downside of our HSS is that it is a so-called private key. What this means is that this HSS shares must come from the same parties in order for them to be evaluated. In other applications, you could think of maybe if different parties could share, do the sharing process locally without communicating with each other, and then still have the servers evaluate functions on the combined shares. This is not the case.
Parties have the same message, but they need to somehow have private randomness.
Yeah, yeah. This is because we need private randomness. Yeah. Cool. And yeah, and also we cannot really certify if the outputs of our HSS is correct or not. In other words, it's not Las Vegas. Yeah. So cool. That's that. I want to talk briefly about how we prove our HSS secure. Security basically just means that the view of any subsets of t-1 parties or less are going to be independent of x, or like they basically hide xi. So the shares consist of these three parts, right? The ciphertext parts and the secret shares parts. The secret sharing part just follows from the privacy of the secret sharing scheme itself. The encryption part follows from security of encryption. But here we have a term where you encrypt something, you encrypt a message that is also dependent on the key. So we need a special kind of security here, known as key-dependent message security. This has a simple proof if we were assuming LWE or LPN, but we're not. We're assuming sparse LPN. And so it does not appear to be immediate. The technical difficulty here is that basically in LWE or LPN, you have random vectors. And if you add two random vectors, the result is a random vector. But if you add two k-sparse vectors, the result is, yeah, it can be anything. At most two k-sparse, yes. But yeah, you don't have good control. We did show that if the field is not binary, then we can salvage this proof with the caveat that now these AIJs will be 2k-1 sparse. Our idea is basically you add two different k-sparse vectors in different ways to make it so that we can hide this key-dependent message. Or an alternative is that we can just do sort of a leveled HSS schemes with a new secret at each level. So now we're no longer encrypting the same secret. We're encrypting the secret of the next level. And so we don't have the circularity issue. Okay. Yeah. And well, what happens if the adversary sees the evaluated output shares? This is sort of a stronger security model for HSS. Okay. where HSS, you're just saying that adversaries can only see some of the shares. But here it can see all of the output shares. And this is actually a realistic threat scenario in some applications.
Oh, but now you're not hiding f of x, you're just hiding x.
Yeah, you're just hiding X. Yeah. But in this scenario, our HSS is not secure. So I just want to say our HSS is secure under one definition, under sort of the standard definition, but it's not secure under this stronger definition, which shows up in some applications, such as in MPC protocols.
You need to make some assumption about f, right? If f is like the identity function,
Yeah.
then nothing can satisfy this.
Mhm.
So it has to be hard, like one way or something.
Yeah, it can be like a simulation-based definition
Okay.
where
Okay.
you reveal nothing more than
I see.
f bytes. Yeah. Okay, and just roughly speaking, this is because the evaluation process of our scheme just evaluates a linear functions on the secret shares. This linear function may depend on f and the ciphertext and so on, but it's still a linear function. And so if we obtain enough of these, then we can solve for the secret shares. And the question here is, can we try to mitigate this error to achieve some downstream applications? One such application is sublinear MPC. And what it is that it basically comes from this circuit size barrier in classic MPC protocols. And with all of these classical protocols, you have to communicate the number of bits that are proportional to the size of the circuit being evaluated. HSS can potentially go beyond this this restriction by having sublinear in the circuit size. And the intuition is quite simple, right? Because HSS, you can do these evaluations locally. And so roughly, you only need to communicate the inputs and outputs if HSS is like ideal. But our scheme is not quite that, so we'll have to put on some bells and whistles. Okay. So the state of the art for these sublinear MPC protocols are quite similar to HSS. There's only sort of a slight improvement over HSS in this somewhat complicated constructions that can achieve 3 or 5 parties, but with the downside of relying on a bunch of different assumptions.
I have a question.
Yeah.
Does the sublinear communication assume that the parties have agreed on a circuit to evaluate ahead of time?
Yes. Yeah.
I know Justin, you got it, right? Okay.
Okay. Yeah. So using our HSS, we can achieve sublinear MPC for arbitrary number of parties. And the communication here is very slightly sublinear. So like basically S over log of S for circuits of size S. Yeah. And we also need to assume the existence of OT because we're working in the dishonest majority setting, but still with semi-honest security. That's it. And OT itself is known from LPN or this specific parameter setting for sparse LPN that also enables public key encryption.
Which is different than the sparse, than the setting you need.
Yeah, which is different from our setting. Yeah. Okay, so as I have mentioned briefly before, the intuition for how HSS can achieve sublinear MPC is quite simple, right? You share your inputs, you evaluate locally, and you share the outputs. Okay, so this gives you very good communications, but this is not quite what we achieve in our HSS. The first issue is that our HSS is private key, meaning that different parties cannot share their inputs and then expect to be able to evaluate on the combined shares. The second issue is that we have an inverse poly reconstruction error. And thirdly, we don't achieve this for every circuit. We achieve it for a very limited class of circuits. And finally, there's sort of something that's inefficient with this, with this template as well. And that is it scales polynomially with the input size. We can try to get it a better dependence on the input size, and actually this better dependence is crucial for making our construction go through. So let me try to address these issues one by one. The private key issue is quite simply addressed by just like running a generic MPC protocol for sharing of all the inputs. Okay. So that's that. The second thing I want to do is reduce this dependence to just linearly in the input size plus some additive terms in the security parameter. And we can do this by doing a hybrid encryption approach, where now you will sort of encrypt using a secret key, and then you will HSS share the secret key. This encryption scheme will be also based on sparse RPN because it also has these nice properties that we need in our final constructions. And so now we will evaluate a slightly augmented circuit C hat, which is first you decrypt and then you apply C. Okay. All right. So that sort of fixes the dependence on the input size to linear. For the reconstruction error, what we basically need to do is we just repeat everything for some kappa, which is super constant times. And then finally, we do a generic MPC for the majority operations, take majority of everything, which would drive down the error to negligible. Finally, to deal with this limited function class, we will use the fact that the circuits we support are Boolean layer circuits. What this means is that it can be split into layers where the wires from the next layer comes from the outputs of the previous layer. And because we have this nice decomposition, we can just split it into chunks of log depth.
Sorry, how is this different from like a L times log depth circuit?
Because like in normal circuits, it could be that you have something in layer 1 connecting to something in layer n. Here, everything like the connection pattern is much more local.
You can't, I mean, you could just have like you could have, oh, so like you could have, no op gates in every layer, but then that counts against the width of the circuit.
Yeah, that counts against the circuit size. Like no ops is yeah. Okay, so what we do is we basically apply our protocol so far for each of these chunks. And the invariance we will maintain is that the outputs of each of these chunks will be secret shares of the inputs for the next chunk. Okay, so then within this evaluation process, we have another augmented circuit, which now first decrypts, then you take majority and you apply the chunk of the circuit. Okay, so then what we get finally is this term, this kappa times size of C over log size of C. Okay, so this is indeed sublinear. If we set kappa to be a small enough super constant and C to be a large enough circuit. Okay, so that's that. Let me recap here. Yeah, so we get sublinear MPC with the slightly sublinear communications from sparse LPN and the existence of oblivious transfer.
Is the oblivious transfer what's used to get the generic?
Yeah, it's for the generic one. So if we work in the honest majority setting, then there are like unconditional MPC protocols, and so we don't need OTs.
Okay. Yeah. I don't quite.
Honest majority just means that you have less than n/2 corrupt parties.
I see.
Yeah, dishonest is when you have majority is when you have more than n/2.
I see.
Okay, Now, with the rest of the time, I'll talk a bit more about the sparse LPN assumptions. So here's a graph of basically the parameter regimes for where prior schemes lie. So this is our HSS schemes. It has K sparsity is poly log n, and the error probability being some inverse polynomial. On another end of the spectrum, we have a constant K, but also with constant noise rates. And these are the constant overheads cryptography primitive applications. And finally, we have this regime here, where with a constant K in inverse polynomial noise rate, but also the number of samples needs to scale or needs to depend on the noise rate as well. So we have this fine trade-off, and we can only achieve PKE with this fine trade-off. Okay, so again, back to this problem with constant K. Well, we have this noticeable distinguishing advantage. So what have prior works tried to do? Well, one way is just to assume a little of one advantage, like a small advantage, doesn't need to be negligible, right? Which is very possible with this. And then for certain primitives, such as PKE, there's a way to amplify PKE with just constant security to PKE with negligible security. Okay, so, but in other schemes, we actually need this negligible distinguishing probability. And in that case, well, one thing we could do is that, let's say we want to actually use these schemes in practice. Then the difference between polynomially small and negligibly small might not be so large after all. We can just try to tune it so that it becomes smaller than some desired parameter that we want. Okay, and this only holds for the setup phase, like this failure probability is only in the initial phase. And finally, we may have some like conjecture, some non-explicit instances of some good matrices. Okay. And actually, in the literature right now, there is this sort of negligible error constructions of such matrices for some polynomial number of samples. But yeah, you can talk to me afterwards if you're interested. Okay. So how does PKE work from the sparse LPN assumptions? Well, first of all, this is a prior scheme back in Aleknovic, and if we just have LPN, then we can achieve this with roughly inverse square root noise. Okay. I won't go over that scheme, but our scheme from sparse LPN sort of takes inspiration from this. So yeah, so this is the parameters needed to get PKE from sparse LPN. And these parameters are so that for matrices A drawn from n times n matrices, there will exist roughly n to the delta sparse vector x in the kernel of A. And so we can now generate A in a planted way so that we know this x. This x will be our secret key. We will encrypt 0 to be a planted instance and 1 to be a random instance. Yeah, and that's basically it for PKE. There's a big open question here is that, can we achieve PKE with better parameter in any form, like super constant K or with slightly larger error probability? Okay. Right, so that will conclude my talk. Let me just summarize the result quickly. We achieve HSS for this non-trivial class of roughly log depth arithmetic circuits with an arbitrary number of parties. And using that, we also achieve sublinear MVC for arbitrary number of parties. And in terms of future directions, I think there are some clear improvements to be made here for our HSS. Can we make it public key? Can we make it completely efficient? And can we realize some downstream applications? Okay. So that's it for me. Thank you.
Thank you.